Welcome back to the channel. In today's video, we're going to do something that's long overdue. I'm going to give you a quick crash course in doing linear algebra in C++ with the Eigen library. And as a demonstration about how to use the library to actually solve a real physics problem, we are going to calculate a quantity that is extremely common to calculate in quantum chaos theory. So without further ado, let's begin by discussing setting up Eigen and actually solving problems with Eigen. So the first thing you're going to want to do, of course, is download Eigen. So you can go just Google Eigen C++. You can either go to their GitLab or to their website and download the Eigen sort of like source files. Eigen is a header-only library, so you don't have to do anything sort of too complicated to get things set up. So here you can just download it by clicking this button, and then let's jump into actually running a basic program that calls Eigen functionality. You see here, I'm using Windows subsystem for Linux. And you can see I already have a YouTube folder set up where I have Eigen already downloaded. So this is the version that I'm using. Whenever you're using this, you should just choose the latest stable release. And you can see this is what the inside of Eigen's sort of folder looks like, where most of the features are in here. So you can see dense, Eigen, things like computing eigenvalues. There's functionality for sparse matrices and so on. So this is a complete linear algebra package, essentially, that is extremely performant. But the thing that I like the most about Eigen is that it's extremely expressive. So let's go into our linear algebra demo, and what I have here is I was doing some tests to make sure things worked. Let's actually delete the executable here. So we have our demo.cpp. To set up a very basic program, you can follow along here. I've included the IO stream, so this is just so we can print things out when we test things. And then just to get us started, I'm including eigen/dense. And what this is going to allow us to do is it's going to allow us to declare matrices that are dense. And what that means is that if I say I want to build a 10 by 10 matrix, a dense matrix will allocate memory and store values in all of the entries. An alternative would be to use a sparse data structure where you only allocate memory to locations that have values. What this basically means is that we're not going to store any zeros. So we have a sparse matrix, we should have a sparse data structure. Today we'll just talk about dense matrices because that's all we need. Now I've set up my file by saying that I'm going to use namespace std. So this is the standard library namespace and the Eigen namespace. And all that means is that actually I don't need this std : It just knows that I'm using the stoi function from the standard. And so this line of code, I've just inserted it. This allows me to read off integers as strings from the command line, which is, of course, we're going to be declaring n by n matrices. So this will just allow us to not have to recompile. I can just pass new n's to the function. Now, of course, we want to be able to compile. So I've quickly made a makefile, which you can follow along and copy this. So the command is demo, and its dependency is demo.cpp. So when we update demo.cpp, the makefile will know that it should recompile if we ask it to. And so I'm using the G++ compiler -03. This is just optimization level 3. And this is how you include Eigen. There's fancier ways to include Eigen, especially if you're using CMake. You can follow their instructions on their website about how to do that. But in principle, all you need to do is include the Eigen, like the path to the directory of Eigen with -i. And then I've enabled two other optimizations, not super important, but -march is equal to native and mtune is equal to native. It's just turning on what are called vectorization features, so they can use like simd instructions and stuff like that when they're doing the computations that you ask it to. And then I'm using the C++ standard 17, not super important, and then I output an executable called demo. So let's get started. Let's say I want to declare a matrix that is, I apologize, I have Copilot on. So Copilot has just autofilled. This is not an advertisement for Copilot, but this is how you declare. This is a real matrix with random entries. It'll fill when I call this command, it will fill the matrix with random entries, and the matrix is n by n. So let's go ahead and print out this matrix just so we can see that we've indeed done that. So to understand this syntax, you should see matrix here. So that's the full word matrix, and then we have a big capital X here. And what the capital X means in the Eigen library is that we're not specifying at compile time how big this matrix is. So I could change this to like a 2, and then it's a 2 by 2 matrix. But we're going to keep this as an X. Now, what D stands for is that it's a double. So the matrix is going to be filled with doubles. So those are 64-bit real numbers. I could change this to a float, then it's a 32-bit number, real number. Or I could say something like CD, and this is a complex double. So it is a complex number where the real and imaginary part are specified by a double. Now, let's just do real numbers for now. So the syntax might feel a little clunky, a little ugly, but you get used to it. I think, like in actuality, it's quite an elegant way to have a strong typing sort of way to declare matrices. So let's compile this and let's output our matrix. And actually, let's clear just because it's starting to get clunky. So demo 2, so that's going to pass, n will be 2, so it'll be a 2 by 2 matrix. You output it like this. Now, an important thing to note about Eigen with its random sort of declarations when you're filling random vectors or random matrices is that you do get these numbers out of a random number generator, but it's deterministic. So these numbers will always be the same. But if I was to then, copy this command and I ask for a matrix B declared in the same way, what you'll find is that, of course, these will not be the same matrix. So I didn't put an extra end line here, but you can see that this is A and this is B, and so these are not the same matrix. So the program will be deterministic. So we can do the same and get some 3 by 3s, etc. So if I rerun this again, of course I'm going to get the same matrices, but of course the two matrices will be different. They'll be randomly generated. Now, what's really nice about Eigen is that the way that these objects interact, let's actually put an end line here. The way that these objects interact is like they are, oh, clock, what is that? Like they are actually matrices. So I can do exactly like A times B, for example, and then I can output that, and let's do that. They behave, you can write basically arbitrary expressions as long as they're valid mathematical expressions for the interaction of matrices with matrices, basically. Right? So you don't have to call functions that are like, matrix multiply A comma B. It's just A times B. And the library knows how to handle this. This is called operator overloading. This is something that, that can be sort of like elegantly implemented if the library authors take the time to do it. So one thing that we can do as well is we can just access entries of the matrix as if they were variables themselves. So we can access the memory directly and make modifications. So this is the 0, 0th entry, and so setting it to 1, we'll see that we actually changed the matrix, I guess what I'm trying to basically demonstrate here is that the matrices behave like matrices, right? So instead of getting this entry, we get 1. Okay, so the next thing that we need is to sort of like understand that we can also just do vectors. So if I write vector xd, and that's we're physicists, let's write psi. Psi here is now a column vector with n entries. In C++, what vector xd and matrix xd actually are is they're templated classes. They're classes, they're objects, and they have member functions. So this guy is not. So this data type is not guaranteed to be normalized, but you can just normalize it. You can say dot normalize, and there we go. Now this is a column vector. We could, for example, make another vector. Let's call it psi2, and it will also be random. And let's also normalize it. Then what we can actually do is we can take. It knows exactly what I want. We can take the inner product. There's 2 ways to take the inner product. You could do psi dot dot like this, psi2, or you can actually do it in the way you would express it mathematically. So it's really up to you. These are equivalent statements. So let's do that, and you can see that we get the same answer, right? So those are two different things. And of course, if these were complex numbers or complex vectors, you could also take the adjoint. You take the adjoint of a matrix. Getting started is very easy. You can write expressions just to show you. For example, psi minus 0.2 times psi2 like this. And the code will know that this is, in fact, multiplying a number into a vector that gives you a vector, multiplying a number into a vector that gives you a vector, and then subtracting off the vectors. It will just process this like it's math, right? And so this is probably something that's probably not super fabulous to you. If you're coming from, let's say, Python or like a higher level language like MATLAB, but this the point is that you can use a low level language like C++, get the speed of C++, while also interfacing with data types that make it feel as trivial as MATLAB. That's sort of the point that I'm trying to make. And there's lots of different things that you can do. For example, and I can't go through all of them. Like, this is just because of how easy this should probably look to you. Getting started should be, very trivial. For example, we could initialize psi instead of a random. We could set it to an all zero vector, or we could set it to a constant, for example. The library is quite large, so I might cover more details about what you can do, or I might solve different problems that expose different features. But for now, this is sort of sufficient for what I want to do in this video. Now, let's actually switch over to physics, and let's do something useful with Eigen. Okay, so let's suppose that we've solved the equation for the energy eigenvalues of the Hamiltonian. So H is just some Hamiltonian, something from quantum mechanics, and these are the energy eigenvalues here. One thing that we're going to assume throughout this is that if I give you EK will be ordered in such a way that it's always less than or equal to EK plus 1, right? So if there's an equal sign, that's a degeneracy in the spectrum. We don't expect many of those, unless it's a very special class of model in the spectrum. So in quantum chaos, we say a model is quantum chaotic if it has EK, it has like spectral statistics such that it looks like random matrix theory, basically. Specifically, if it looks like the Gaussian orthogonal ensemble or the Gaussian unitary ensemble. And what I mean by that is that when I take When I take random matrices, you can think of this, for example, as generating matrices randomly with random Gaussian coefficients. When I look at the spectral statistics or the properties of the spectrum on average of a matrix like this, and I look back at my physical Hamiltonian, they look remarkably similar, and we call this property quantum chaos. There's a whole history to this. Basically, it's founded in the idea that if you take a classically chaotic Hamiltonian and you quantize it, this is what you find, basically. This is what you find. The typical markers of classical chaos don't particularly survive or play well with quantum mechanics because of unitarity. There's a whole literature and there's lots of concepts and questions and directions of the way people are trying to think about these things. But this is sort of like the standard go-to definition of quantum chaos. And so today what we're going to do is going to diagonalize a Hamiltonian. We're going to cheat a little bit where we're actually just going to we're going to generate one example of a of sort of like a Gaussian filled matrix, and then we're going to calculate a quantity that you would often find in physics. Okay, so what are we going to calculate? The thing that we're going to calculate is first we need to introduce the gaps. Okay, so Sj is a gap, and the gap is defined like this. And due to our definition, we know that this is greater than or equal to 0. Now, we're not going to calculate the statistics on Sj because there's a slightly better quantity to choose, and that is the ratio statistics, or the ratio quantity of the gaps. And so the ratio, this is called the ratio test, is calculating all of these values. So on top you put the minimum of Sj plus 1, and on the bottom you put the maximum of Sj plus 1, and you can see right away that this is in sort of all of the ratios will be on the interval 0 to 1. A very standard thing to do with these numbers is then to compute their average. And random matrix theory makes a very concrete prediction about what this average is, and it helps us distinguish quantum chaotic models from non-quantum chaotic models. So I'm going to quickly jump over to my recent paper that used this technique. And so you can see Rj here is exactly as I defined it to you. And if you use a Gaussian orthogonal ensemble and you do the analytics for 3x3 matrices, you see that the actual distribution of ratios is given by equation 12. And if it's instead sort of like a Poisson type model, an integrable type model, instead you would find this ratio distribution. We're not going to calculate the distributions, we're going to calculate the averages, which we state here in the text. And so basically, if the model is quantum chaotic, what we should find is good agreement with this number. So the average of the ratios should be 4 minus 2 times the square root of 3, which is approximately this number in decimal form. So this, we're going to try and do this. Now that we have our sort of physical context and motivation, let's now write a function to generate a matrix. Now, we can't actually rely on Eigen's random generator here, and that's because these entries are uniform. And the Gaussian matrix, so we want Gaussian entries with 0 mean and unit variance. All right, so that's very specific, and of course we want a Hermitian matrix, so it looks like a Hamiltonian, right? So that's what we're comparing. And because specifically it's a real, yeah, Copilot guess, because it's a real matrix, it's going to be a real symmetric matrix. Okay, so let's get on that. and we'll create a function that returns that type of matrix. So we're going to return a matrix XD, and did it just do it? Is that right? Right. So we're going to return a matrix XD that is n by n. Okay, so that should be like that. So it's going to be an n by n 0 matrix, and this is exactly how I would have done it. So yeah, we want a normal distribution that spits out doubles. That has, this is where the mean goes, and this is where the variance or the standard deviation, it doesn't matter if it's 1. And then, okay, so then we're going to loop over the matrix and fill it with random entries. Okay, so if we call this function, yeah, we're going to do that. But we're actually going to call the Hamiltonian like that specifically. So we're going to add A to its transpose, and that should give us a Hermitian or a real symmetric matrix. Now I'm going to add 2 headers. Specifically, we're going to add random here so that this works. And the next thing that we're going to add is eigenvalues so that we can actually solve the Hamiltonian for its spectrum. So the way that we'll do this is, wow, it's just telling me the way. Wow. Okay. So I don't know if this is helpful, the fact that I'm letting Copilot actually do this code for me. So basically, we're going to call the self-adjoint eigensolver, and the way this method works is you have to tell it here. So this is templated. So it's an eigensolver that can basically do the problem, but you have to tell it which data type it's doing it to. So I could, for example, do floats here, or I could do complex doubles, or I could do complex floats, right? So we're doing matrix XD because that is the matrix that we're working with. And right here, this is, it will compute the eigenvalues, and right now with the way it's written, it will also compute the eigenvectors. So we want eigenvalues only, and there's a reason for this. One, eigenvectors are a lot of memory, so you should always be memory cautious. And eigenvalues only is faster, basically. So if I only need the energy eigenvalues, then it's always best to only compute eigenvalues. So why don't we do this quickly, and let's print out. So to get the eigenvalues, you do exactly what, you don't even need me. Just let Copilot write the code for you. Let's print out these eigenvalues, and let's compile. Let's make sure we didn't do anything wrong. Or this, right? I guess it would be a Copilot doing things that are wrong. Okay, let's do 4 by 4, right? Okay, so an interesting thing to note here is that Eigen will return to you eigenvalues that are ordered. And the way that we wrote this is it's not deterministic, right? So every single time we give the random number generator a new seed, because this is what this random device is. Okay, so now that we have the eigenvalues, we want to compute the ratio, right? And to do that, let's make a function. So we're going to compute ratio between 2 numbers, double A, double B, and I'm going to be a little bit lazy here, and I'm not going to look at edge cases. So I think what Copilot is doing here is that, like, I went through the example previously just to make sure, like, everything sort of worked out. And basically, I'm not going to handle any edge cases. I'm just going to say, okay, so if A is greater than B, then we know that our condition says b divided by a for the ratios. This is how we defined it. And if not, if b is actually greater than a, we're just going to return this. And I guess this else will handle like sort of all other cases. So the less than or equal will also return this. Now the thing is that this is lazy. But it's a demo, true. Basically, we should be suspicious of very small numbers here that are essentially 0, but they're non-zero because of numerical precision issues or little things like that. So we could end up getting some weird result because we're not actually computing things well here. The next thing that we're going to do is we're going to calculate the gaps. Okay, so what I'm going to do here is I'm also going to be what does it say? Anyways, so we're going to output a vector xd of all of the gaps. So what we know is that there will be one less gap than there are eigenvalues, and we're going to pass the eigenvalues to the vector, or sorry, to the function in this way specifically. So I say const because we're not going to change eigs. This allows optimizations to be done, and I'm going to pass with an and here, which is pass by reference. So there's no copying. I'm not copying this data into this function. I'm giving this function direct access to the memory, but I'm also saying, but you're not allowed to change it, basically. That's all this is doing. And so this is good practice. You should never, if you can avoid copying, you should always avoid copying. Copying data, unless it's small data, like a single double or something like that, that's always super inefficient. So the dimension or the number of eigenvalues that we have is eigs.size. So this tells you how big the vector xd is, very useful. And we're going to calculate all of the gaps. We just quickly loop through them with a for loop. And we're just going to fill the entries here, eigs m+1 minus eigs m, right? And then we return gaps. And so when I call this, it will return to me a vector xd. Finally, what we're going to do is we are going to calculate the average of the ratio, right? So the first thing I'm going to do is I'm going to calculate all of the gaps. I'm going to pass the eigenvalues in the exact same way, and just because we're up here, I'm going to return a double because I'm returning the expectation value of r, basically. Sure. So here, the first thing we do is we're going to calculate all of the gaps, and then again, the number of ratios is 1 minus the total number of gaps, and that's because each ratio has 2 of these neighbors inside the expression. So this time we're actually going to do a sum, and we know that the number of ratios, so if we're going to compute the average, then we're going to weight that sum by 1.0 divided by num ratios. This 1.0 is just there to avoid this thinking that this is integer arithmetic, integer division, right? And so basically, we're just going to go through and we're going to compute the ratio of all of the gaps, basically. And then we're going to return the sum. So let's comment this out. This basically solves our problem though, right? So I'm going to set the precision to 8 for cout. That's basically because I have that many digits here. And so this is the theory. This is the expected value. And we're going to calculate what our average ratio is for one realization of the Hamiltonian. Now, I want you to sort of like think about that for a second. When I told you that's what the GOE statistic is, you should have noticed that there's like this. The interesting thing here is like that's averaged over many matrix realizations, but these problems have something that's called typicality. And typicality basically says that for this measure, it's not just that on average these matrices will have this property, it's also that if you pick out one matrix, it will also with high probability have this property already on its own. So the distribution is very tight and sharp. And not all things have this property. So for example, if you do the spectral form factor calculations, those don't have a property that's called like self-averaging. You do have to perform averages and like all of these things, different realizations and averaging over different realizations to get the, the predictions of random matrix theory. But this specific example actually doesn't have that property, which is quite interesting. Okay, so this should give us something that's like relatively close to theory, especially as we increase n here. Actually, haven't tested this, but this is my expectation. Demo, and let's do 10. Okay, so it's very different, but the model size is not that big. So let's do 100. Okay, we're getting closer. Let's do 500. Okay, very, very close. Let's do 800. Okay, kind of slipped away. If we do it again, okay, so it's close. So maybe for smaller sizes, you need a little bit more averaging. If we don't get good agreement, then... Okay, there you go. So now we have 2 digits of precision for 1200. Let's go up to 2000. We're almost I would call that a little bit of convergence. Let's do 4000, which will be a little slow. Diagonalizing a matrix is computationally complex. It's sort of n to the 3. Yeah, so we're a little farther away. Maybe we do need a little bit more averaging. So if we do it again, farther away. Okay, so let's like briefly move on. Do something that will take a little bit of time. Let's do 8,000. Okay, so we got this answer back. It's not particularly better. So I think what we'll do is we'll add a little bit of averaging. Like in principle, yeah, so let's add a little bit of averaging to see if we can get a little bit of better agreement with this. So it's not as typical as I sort of expected. It's not as typical as I expected, but it shouldn't be too hard to get agreement. So let's do something like okay, so yeah, so theory is there. And what we're going to do is we're going to say the average is equal to 0, and then we're going to do int samples, and let's just do 100. So for int m is equal to 0, m is less than samples, m plus plus. What we'll do is we will generate these on the fly. So in each iteration, we'll get a new matrix, and we will solve that matrix also on the fly, of course. And then the average will be plus equals 1.0 divided by samples times, yes, the average, like that. And then at the end, we'll change this to average here. And actually, let's make samples something that we can pass to the... Yeah, we'll do the second entry like that. So we have to pass how big we want the matrix and how many samples we want. Okay, so clearing, let's do demo, and we'll do 1,000 by 1,000 matrices, and let's quickly warm up with 100 samples. So that's theory. Let's hope this doesn't take too long. Okay, so that looks pretty good. I mean, if I made it smaller and then I just did like 1,000 samples. So certainly isn't as typical as I expected. Maybe there's something wrong with the way I'm generating the matrix. Let's do something smaller, and let's see if like increasing the samples by a lot helps. This is really surprising because when you have a physical Hamiltonian, you get agreement quite quickly. So for example, if you look at our if you look at our article, so we're not averaging over anything. So this is our physical Hamiltonian, and it's spectral statistics. We're not averaging over anything, and we're getting like pretty close agreement. I guess it's not like overly. It is kind of. It's. I think we're closer with a single shot of the random matrix model. But so L is equal to 24 is a very big spectrum. Okay, so we're getting about here. Let's do 2000, and we'll do 50. Is it the system size maybe? If we get 3 digits, I'm ending the video. That's enough for me. Okay, so we're almost in agreement. There's probably issues and some interplay between how big the system is and how many samples we get. And so I'm basically going to leave it here just because it's not uber important that we get the exact right answer. The typicality, I mean, this is interesting that you only need 10 samples to get close to the average for sufficiently large system sizes. Your prediction is a little bit worse for smaller matrices and even more samples. But I'm going to leave it here. If you made it this far, I hope you enjoyed this format. And I hope you got some value out of the video. So I'll see you in the next video, in the next time. So don't forget to like, subscribe, and leave a comment below.